Imagine standing at the edge of the ultimate abyss. Not just a hole in the ground, or even a chasm in space, but a tear in the very fabric of reality itself. A place where the laws of physics don't just bend, they shatter. Where time becomes meaningless, where space folds in on itself, where the universe as we know it simply stops making sense. This is a singularity, the heart of a black hole, the most extreme environment that exists anywhere in the cosmos. And tonight we're going to journey there together. You might think you know about gravity. You feel it every single day. But what you experience here on Earth is gravity at its gentlest. Out there in the darkness of space, gravity becomes something else entirely. Something so powerful it can trap light itself. Something so intense it can tear the fabric of space and time into pieces. By the end of our journey tonight, you'll understand something that even Einstein himself struggled to accept. You'll peer into the cosmic abyss where all of our scientific understanding reaches its absolute limit. You'll discover what happens when the universe breaks. The question isn't just what happens to matter near a singularity. The question is what happens to reality itself. Chapter 1. Gravity in our daily lives. Let's start with something simple. Something you've experienced your entire life without even thinking about it. Right now, as you sit or stand wherever you are, you're experiencing gravity. It's pulling you downward toward the center of the earth. It's what keeps your feet on the ground. Drop a ball and it falls. Simple, right? That ball accelerates downward at a steady rate. No matter how many times you drop it, it behaves the same way. This predictability is what makes gravity seem so straightforward, so ordinary. But look closer. Gravity isn't just pulling that ball down. It's pulling on everything around you. The chair you're sitting in, the air you breathe, the water in the oceans, even the atmosphere that wraps around our planet like a blanket. Without gravity, all of it would drift away into space. Think about the moon hanging in the night sky. What keeps it there? Why doesn't it just fly off into the darkness? Gravity. The Earth pulls on the moon, and the moon pulls back on the Earth. That mutual pulling creates the orbit we see every night. The moon is actually falling toward Earth constantly, but it's also moving sideways fast enough that it keeps missing us. That's what an orbit really is, a continuous fall that never quite reaches the ground. The tides rising and falling in our oceans, that's gravity too. The moon's pull is stronger on the side of Earth facing it, so water bulges outward. As our planet rotates beneath this bulge, we see tides rise and fall in an eternal rhythm that has continued for billions of years. For centuries, we thought we understood gravity completely. Isaac Newton gave us the math in 1687. His law of universal gravitation said that every object with mass pulls on every other object with mass. The bigger the masses, the stronger the pull. The farther apart they are, the weaker the pull. Simple, elegant, and it worked. Newton's equations let us predict the motion of planets with incredible accuracy. We could calculate when eclipses would happen decades in advance. We could send rockets to the moon and know exactly where the moon would be when they arrived. For almost 250 years, Newton's gravity was considered one of the most perfect theories in all of science. But there was a problem. A tiny discrepancy that nobody could quite explain. And that small crack in Newton's perfect theory would eventually lead us to something far stranger, far more wonderful, and far more terrifying than anyone had imagined. Chapter 2. Einstein's revolutionary idea. In 1905, a 26-year-old patent clerk in Switzerland published a paper that would change everything. His name was Albert Einstein, and he had been thinking about light. What he discovered would completely overturn our understanding of space, time, and gravity itself. Einstein asked a deceptively simple question. If you were riding on a beam of light, what would the universe look like? This thought experiment led him to a shocking conclusion. The speed of light is absolute. No matter how fast you're moving, no matter in what direction, light always travels at the same speed relative to you. Always. But if the speed of light never changes, something else has to give. And what gives is space and time themselves. They're not fixed, unchanging stages where events happen. They're flexible, malleable. They can stretch and squeeze and warp. Space and time aren't even separate things. They're woven together into a single fabric that Einstein called space-time. Imagine a vast rubber sheet stretching out in all directions. That's a simple way to picture space-time, though the real thing exists in 4 dimensions, not 2. 3 dimensions of space that we can move through, plus 1 dimension of time that we all travel through at different rates. Here's where it gets interesting. Put a heavy object on that rubber sheet, and what happens? It creates a dip, a depression. The sheet curves downward around the mass. Now roll a marble past that depression. The marble's path bends. It curves toward the heavy object. Not because the heavy object is reaching out and pulling it, but because the marble is following the curves in the sheet itself. This is Einstein's revolutionary idea about gravity. Gravity isn't a force at all. It's geometry. Mass tells space-time how to curve, and curved space-time tells matter how to move. The Earth doesn't pull the moon with some mysterious force reaching across empty space. Instead, the Earth's mass creates curves in space-time, and the moon simply follows those curves like a ball rolling along a warped surface. Think about what this means. When you drop that ball we talked about earlier, it's not being pulled downward by Earth's gravity. The ball is traveling in a straight line through space-time. It's just that space-time itself is curved near Earth's surface, so straight lines point downward. And here's something even stranger. Time itself bends near massive objects. If you could place 2 identical clocks side by side, then lift one of them to the top of a mountain while leaving the other at sea level, the clock on the mountain would tick slightly faster. Not because there's anything wrong with the clock, but because time itself runs at different rates depending on how curved space-time is around you. This isn't just theory. This is real. The GPS satellites orbiting above your head right now have to account for this effect. Their clocks run faster than clocks on the ground because they're farther from Earth's mass, where space-time is less curved. If we didn't correct for this, GPS directions would be off by miles within just a few days. Einstein published these ideas in his theory of general relativity in 1915, and the world of physics would never be the same. But even Einstein had no idea just how far his equations would take us, or what horrors they would predict. Chapter 3. Testing Einstein in the Real World. When Einstein first proposed his theory, many scientists were skeptical. Sure, the mathematics was beautiful, but did it actually describe reality? Science demands evidence, and Einstein's theory made specific predictions that could be tested. The first piece of evidence had actually been sitting there for decades, waiting for someone to explain it. Mercury, the innermost planet in our solar system, had been misbehaving. Its orbit around the Sun wasn't quite what Newton's equations predicted. You see, Mercury doesn't orbit in a perfect circle. Its orbit is an ellipse, an oval shape, and the point where Mercury comes closest to the Sun, called the perihelion, slowly rotates around the Sun over time. Newton's equations predicted how fast this rotation should happen based on the gravitational tugs from other planets. But Mercury's perihelion was rotating 43 seconds of arc per century faster than Newton's math said it should. 43 seconds of arc doesn't sound like much. That's barely more than the width of a human hair seen from across a room. But in the precise world of celestial mechanics, it was a glaring discrepancy. Astronomers even wondered if there might be an undiscovered planet closer to the Sun, pulling on Mercury. They called this hypothetical planet Vulcan. Einstein's equations solved the mystery instantly. When he applied general relativity to Mercury's orbit, accounting for the way the Sun curves space-time, the orbit came out exactly right. No mysterious hidden planet needed, just curved space-time. When Einstein calculated this in November of 1915, he later said his heart palpitated with excitement. He knew he had something real. But the most dramatic test came 4 years later during a total solar eclipse. Einstein's theory predicted that light from distant stars should bend when it passes near the Sun. The Sun's mass curves space-time, and light, like everything else, follows those curves. During a total eclipse, when the Moon blocks the Sun's glare, stars near the Sun's edge become visible. If Einstein was right, those stars would appear shifted from their normal positions. On May 29, 1919, astronomer Arthur Eddington led an expedition to the island of Principe off the coast of Africa. As the Moon's shadow swept across the island and darkness fell in the middle of the day, Eddington photographed the stars around the eclipsed Sun. When he compared these photos to pictures of the same stars taken at night months earlier, the stars had shifted by exactly the amount Einstein predicted. The news made headlines around the world. "Einstein overthrows Newton," declared the papers. Overnight, Einstein became the most famous scientist on Earth. His wild hair and gentle demeanor made him a celebrity, but it was the power of his ideas that truly captivated the world. Since then, we've tested general relativity in hundreds of ways, and it passes every single test. We've measured gravitational time dilation with atomic clocks on airplanes. We've watched pulsars, spinning stars that act like cosmic lighthouses, and their behavior matches Einstein's predictions perfectly. We've even detected ripples in space-time itself, gravitational waves, just as Einstein's equation said must exist. In 2015, the LIGO Observatory detected gravitational waves from 2 black holes colliding over 1 billion light-years away. The space-time around those black holes was so violently warped that it sent shockwaves through the entire universe. Every test confirms what Einstein told us. Space-time is real. It can bend, twist, and ripple. And the more mass you have concentrated in one place, the more dramatically space-time curves. But what happens when you push this to the absolute extreme? What happens when you concentrate so much mass into such a small space that space-time doesn't just curve, it collapses in on itself? That's where our story gets truly strange. Chapter 4. The Birth of Black Holes. Stars are cosmic power plants, and they run on nuclear fusion. Deep in the core of every star, hydrogen atoms are being crushed together with such force that they fuse into helium, releasing tremendous amounts of energy in the process. This energy rushes outward, creating the pressure that holds the star up against its own gravity, trying to crush it inward. It's a delicate balance. Gravity pulling in, fusion pressure pushing out. As long as the fusion continues, the star remains stable. Our Sun has been in this balance for nearly 5 billion years, and it will continue for another 5 billion more. But nuclear fuel doesn't last forever. Eventually, every star runs out of hydrogen in its core. What happens next depends entirely on how massive the star is. If the star is relatively small, like our Sun, it will gently expand into a red giant, puff off its outer layers, and settle down into a white dwarf. A white dwarf is incredibly dense, about as massive as the Sun, but squeezed into a sphere the size of Earth. A teaspoon of white dwarf material would weigh as much as an elephant. But there's a limit to how massive a white dwarf can be. Above about 1.4 times the Sun's mass, the pressure from electrons trying to stay apart isn't enough to hold the star up anymore. For more massive stars, the collapse continues. Electrons get crushed into protons, forming neutrons. What you get is a neutron star, even denser than a white dwarf. Now a teaspoon of material weighs as much as a mountain. The entire mass of the Sun compressed into a sphere just 12 miles across. Neutron stars are so dense that a sugar cube of neutron star material would weigh more than all of humanity combined. But there's a limit here too. Above about 3 times the Sun's mass, even the neutrons can't hold the star up. And when this limit is exceeded, nothing in the entire universe can stop what happens next. The collapse continues, and continues, and continues. The star's core crushes down smaller and smaller, past the size of Earth, past the size of a city, past the size of a mountain. The matter gets denser and denser. Space-time curves more and more steeply around it. And then something extraordinary happens. Space-time curves so steeply that it closes off completely. A boundary forms, a point of no return. Light that crosses this boundary can never escape back out. It's trapped forever. This boundary is called the event horizon, and once it forms, you have a black hole. The name is perfectly literal. It's a hole in space that is utterly, completely black. No light escapes from it because light can't climb back up the infinitely steep curve in space-time. To an outside observer, the black hole is absolutely dark, a sphere of pure blackness against the stars. The first person to discover black holes lurking in Einstein's equations was a German physicist named Karl Schwarzschild. He made this discovery in 1916, just months after Einstein published general relativity, while serving as a soldier in World War I. Schwarzschild found an exact solution to Einstein's equations for a simple case, a perfectly spherical, non-rotating mass. And his solution showed that if you compressed any amount of mass into a small enough volume, you would create an event horizon. You would create a black hole. When Einstein learned of this solution, he was troubled. Yes, the mathematics worked out, but surely nature wouldn't actually do this. Surely something would stop the collapse before it got that extreme. Black holes were just a mathematical curiosity, not real objects that could exist in the universe. But Einstein was wrong. Nature doesn't care about our sensibilities. When a massive star runs out of fuel, collapse is inevitable. The black hole will form. And we now know the universe is full of them. There's one at the center of our own galaxy, weighing as much as 4 million suns. There might be 100 million black holes scattered throughout the Milky Way alone. And each one of these black holes contains, at its very center, something even stranger than the black hole itself. At the center sits the Singularity, a point where all the collapsed mass resides, where space-time curvature becomes infinite, where the laws of physics, as we know them, simply break down. Chapter 5. Anatomy of a Black Hole. Before we can understand what happens, at a singularity we need to understand the structure of a black hole. Because a black hole isn't just a simple object. It has an architecture, a geometry that defies our everyday intuitions about space and time. Let's build a black hole from the inside out. At the very center sits the singularity itself. We'll come back to this mysterious point later. For now, just know that all the mass of the collapsed star is concentrated there, in a region of zero volume. All of it. Extending outward from the singularity is the event horizon. This is the boundary we've been talking about, the point of no return. The event horizon is not a physical surface. There's no wall there, no membrane, no barrier you could touch. It's simply a place in space-time where the curvature becomes so extreme that all forward-pointing paths lead inward and downward toward the singularity. Once you cross the event horizon, your future must contain the singularity. There's no path that leads back out. The size of the event horizon depends on the mass of the black hole. More mass means a larger event horizon. The relationship is beautifully simple. For every mass equal to our Sun, the event horizon has a radius of about 3 kilometers. Double the mass, double the radius. This critical radius is called the Schwarzschild radius, named after the man who first calculated it. A black hole with the mass of our Sun would have an event horizon about 6 kilometers across. That's tiny compared to the Sun's actual size of about 1.4 million kilometers across. The Sun contains enough mass to form a black hole, but it's spread out over such a vast volume that the curvature it creates in space-time is relatively gentle. For a supermassive black hole, like the one at the center of our galaxy, containing 4 million solar masses, the event horizon is about 12 million kilometers in radius. That's big enough to swallow dozens of stars the size of our Sun. Yet even this enormous sphere is vanishingly small compared to the galaxy itself. Here's something crucial to understand. The event horizon is not an edge at the surface of the black hole. It doesn't mark where matter ends. The event horizon is simply a property of space-time itself. It's the place where space-time has curved so steeply that escape velocity exceeds the speed of light. Think about escape velocity for a moment. On Earth, if you want to throw something into space so it never falls back down, you need to throw it at about 11 kilometers per second. That's Earth's escape velocity. On the Moon, with less mass and weaker gravity, escape velocity is only about 2.4 kilometers per second. As you add more mass or compress it into a smaller volume, escape velocity goes uppy. At the event horizon, escape velocity reaches 300,000 kilometers per second. That's the speed of light. And since nothing can move faster than light, nothing can escape. Not matter, not energy, not even information. Once you cross the event horizon, you are cut off from the rest of the universe forever. Beyond the event horizon, extending outward to infinity, is ordinary space, though space strongly curved by the black hole's gravity. If you stay outside the event horizon, you're safe. You can orbit the black hole just like a planet orbits a star. You can even hover at a fixed distance using rocket engines, though the closer you get, the more thrust you need. This is the basic anatomy: singularity, event horizon, external space. But the real complexity emerges when we consider what happens at each of these regions, when we ask what an observer actually experiences. Because it turns out that what you see depends entirely on where you are and whether you're falling in or watching from outside. Chapter 6. Approaching the Event Horizon. The Outside Observer. Let's conduct a thought experiment. Imagine you have a friend, let's call them Alex, who has volunteered for a one-way mission to study a black hole. You're staying safely outside in your spaceship, hovering many thousands of kilometers from the event horizon. Alex is falling inward in a smaller probe, sending back radio signals describing what they experience. At first, everything seems normal. Alex falls faster and faster toward the black hole, accelerating under what appears to be ordinary gravity. You watch through your telescope and track the probe on your instruments. Radio signals come back clearly. Alex describes feeling weightless, in free fall, with the black hole growing larger in the window. But then you notice something ODD. The radio signals are arriving slightly slower than before. And when you check the frequency, you find they've shifted toward the red end of the spectrum. The signals are red-shifted. This is gravitational redshift in action. As radio waves climb up and out of the deep gravitational well around the black hole, they lose energy, which means their wavelength stretches out. The closer Alex gets to the event horizon, the more extreme this effect becomes. The radio signals arrive more and more slowly, and here's where it gets truly strange. When you look at your clock tracking Alex's mission time, you notice that according to your clock, Alex seems to be slowing down. They're falling more and more slowly, taking longer and longer to cover each successive kilometre toward the event horizon. Alex's clock, which appears in the video feed from the probe, also seems to be running slow. Minutes on their clock correspond to hours on yours, then days, then weeks. The closer they get to the event horizon, the more extreme the time dilation becomes. And as Alex approaches the exact location of the event horizon, something remarkable happens. From your perspective, they stop. They appear to freeze at the horizon, hanging there for eternity. Their clock stops ticking. The light from their probe gets redshifted more and more, sliding down through red, through infrared, through radio waves, until it becomes so stretched out that you can't detect it anymore. Alex fades to black. But here's the crucial thing to understand. Alex never disappears in an instant. From your viewpoint, Alex approaches the horizon asymptotically, getting closer and closer, but never quite reaching it. If you could watch forever with perfect instruments, you would see Alex getting dimmer and dimmer, more and more frozen in time, but always still there, painted forever on the event horizon. This is not an illusion or an optical trick. From the perspective of an outside observer, it genuinely takes infinite time for anything to cross the event horizon. You will never see Alex cross it. You will never receive a signal from them saying they've made it through. The last signal you receive will be from infinitesimally close to the horizon, stretched out and redshifted until it's undetectable. Every black hole is therefore surrounded by a ghostly image of everything that ever fell into it, frozen at the moment of crossing, fading slowly into invisibility. Every atom of every star that collapsed to form the black hole, every bit of gas that spiraled in later, all of it remains visible, in principle, hovering at the horizon forever from the perspective of the outside universe. This seems paradoxical. How can Alex both cross the horizon and not cross it? The answer is that there's no single objective answer to the question, has Alex crossed the horizon? The answer depends on who's asking and where they are. For you outside, the answer is no, and it always will be no. But for Alex, the story is completely different. Chapter 7. Crossing the Event Horizon, the Infalling Observer. Now let's rewind and experience the same journey from Alex's perspective. This time, you're not watching from outside. You're sitting in the probe, falling toward the black hole, watching the universe around you. Your journey starts the same way. You fall faster and faster, watching the black hole grow in your window. You feel weightless, just like an astronaut in orbit. Your instruments work normally. Your clock ticks normally. Everything seems fine. As you fall deeper into the gravitational field, you notice something strange happening to the universe behind you. Light from distant stars appears blue-shifted, compressed to shorter wavelengths. And time in the outside universe seems to be speeding up. Your friend's spaceship, hovering safely far away, appears to be moving in fast forward. This is the flip side of the time dilation effect. From the outside observer's view, your clock runs slow. From your view, their clock runs fast. Both perspectives are equally valid. This is the relativity in Einstein's theory. You continue falling. The event horizon approaches. You brace yourself for something dramatic, some clear indication that you're crossing this famous boundary. You check your instruments carefully, watching for any sign. And then the moment comes. You cross the event horizon, and you feel nothing. There's no wall, no barrier, no sudden change. The crossing happens smoothly and unremarkably. Your clock keeps ticking at its normal rate. Your instruments continue working. The probe's hull remains intact. To you, locally, space-time seems perfectly ordinary. You've crossed the point of no return, and you didn't even feel it. This is one of the most counterintuitive facts about black holes. The event horizon is not locally special. If you fell through the event horizon of a sufficiently large black hole, like a supermassive one, you might not even know you'd crossed it until you tried to turn around. And that's when you discover the horrible truth. You're now inside the event horizon. You try firing your rockets to escape. You point your engines toward the outside universe and fire at maximum thrust. But no matter how powerful your engines, no matter which direction you point them, you can't escape. You can slow your fall toward the singularity slightly, but you can't reverse it. The singularity lies in your future, as inevitably as tomorrow lies in the future of someone on Earth. Think about that. Inside the event horizon, the singularity is not a place ahead of you that you're falling toward. It's a moment in time that lies ahead in your future. You can no more avoid reaching the singularity than you can avoid the next second on your clock. Time itself has become directional in a way that points only inward. Looking back toward the outside universe, you see something extraordinary. Through the probe's rear window, you see the entire future history of the universe, compressed into a shrinking circle of light. Stars age and die in fast forward. If you watched long enough, you might see the sun exhaust its fuel and expand into a red giant billions of years from now, all in the span of seconds from your perspective. But you don't have long enough to watch, because ahead of you, unavoidably, inevitably, lies the singularity, and your journey isn't over yet. Chapter 8. Spaghettification, Tidal Forces. Before we reach the singularity, there's one more force you need to understand. Actually, it's not really a new force at all. It's a consequence of gravity that we've been ignoring up until now. It's called tidal force, and near a black hole, tidal forces become absolutely devastating. You experience tidal forces every day, though they're far too weak to feel. Here on Earth, your head is slightly farther from the center of the planet than your feet. That means gravity pulls on your feet slightly more strongly than on your head. The difference is absolutely tiny, but it's real. The Moon experiences much stronger tidal forces from Earth. The side of the moon facing Earth feels slightly stronger gravity than the side facing away. This difference creates stress in the moon's rock, generating a tiny bit of heat through friction. The same tidal forces acting on Earth's oceans create the tides that give this force its name. Near a black hole, tidal forces become extreme. Remember, gravity gets stronger as you get closer to a massive object, and the rate at which gravity changes with distance gets more and more dramatic as you approach a black hole. Let's say you're falling feet first toward a black hole. Your feet are closer to the singularity than your head, so they feel stronger gravity. They're pulled downward more forcefully than your head. This creates a stretching force along the length of your body. At the same time, imagine your arms stretched out to your sides. Your left hand and right hand are roughly the same distance from the singularity, but they're being pulled in slightly different directions, both toward the center. This creates a squeezing force, compressing you from the sides. The result is that you get stretched lengthwise while being compressed from the sides. Scientists call this process spaghettification, and the name is grimly appropriate. Your body would be stretched like a noodle while being squeezed thinner and thinner. For a stellar mass black hole, the kind formed from a single massive star, tidal forces become lethal long before you reach the event horizon. At just a few hundred kilometers from the horizon, the difference in gravity between your head and feet would be enough to tear your body apart. Your bones would snap, your flesh would rip, you'd be pulled into a long, thin stream of atoms spiraling into the black hole. But here's where size matters. For a supermassive black hole like the one at the center of our galaxy, the situation is different. The event horizon is so large, millions of kilometers in radius, that tidal forces at the horizon are actually quite gentle. You could cross the event horizon completely intact, feeling nothing unusual at all. This might seem counterintuitive. How can a more massive black hole have weaker tidal forces? The answer lies in how far you are from the singularity when you cross the horizon. For a supermassive black hole, the event horizon is very far from the singularity, so the curvature of space-time changes relatively slowly across your body's height. For a stellar mass black hole, the horizon is very close to the singularity, so space-time curves much more steeply. But don't get comfortable. Even in a supermassive black hole, tidal forces grow rapidly as you fall inward from the event horizon. The closer you get to the singularity, the more extreme they become. Eventually, inevitably, you reach a point where the tidal forces are strong enough to rip you apart. First, your body tears. Then your organs separate. Then your cells rupture. Then your molecules break. Then even atoms get pulled apart into subatomic particles. And still you fall toward the singularity, now just a stream of quarks and electrons, still being stretched and squeezed by forces growing without limit. This is the doom of everything that crosses an event horizon. Not a quick, merciful destruction, but a slow, inevitable shredding by tidal forces that grow stronger with every passing moment. The event horizon is the point where escape becomes impossible. The singularity is where destruction becomes inevitable. And it's at the singularity itself where things become truly incomprehensible. Chapter 9. What is a singularity? We've finally arrived at the heart of the mystery, the singularity. This word gets thrown around a lot, but what does it actually mean? What happens to space-time at this infinitely curved point? Let's start with what we can calculate. When we solve Einstein's equations for a black hole, they tell us that all the mass that formed the black hole gets concentrated into a single point. Not a small point. Not a tiny ball of incredibly dense matter. An actual geometric point with zero size, zero volume, infinite density. Think about what that means. Take all the mass that made up the original star, perhaps 10 or 20 or 50 times the mass of our entire sun. Every atom, every proton and neutron and electron that made up that star. Now concentrate it into a point with zero diameter. The density becomes infinite. Infinite density sounds like science fiction, but it's what the mathematics tells us. When you have any finite amount of mass divided by zero volume, the result is infinity. And this isn't just big or really big or unimaginably big. It's actually infinite, limitless, unbounded. But there's more. At the singularity, space-time curvature also becomes infinite. Remember our rubber sheet analogy? Imagine the dip created by a mass getting steeper and steeper and steeper until it becomes a perfectly vertical drop, and then curves beyond vertical, beyond any steepness you can imagine. The curvature diverges. It goes to infinity. When physicists encounter infinities in their equations, it's usually a red flag. Infinities often mean that our theory has broken down, that we've pushed it beyond its domain of validity. It's like dividing by zero on a calculator. You get an error because the operation doesn't make sense in that context. But with black hole singularities, we can't just wave away the infinities as errors. The entire solution, from far outside the black hole all the way down to the singularity, comes from the same equations. If we trust Einstein's general relativity outside the black hole, and we do because it's been tested extensively, then we have to take seriously what it tells us happens at the center. Now, there are actually two types of singularities predicted by general relativity. The type depends on whether the black hole is rotating. A non-rotating black hole has what's called a point singularity. This is the simplest case, the Schwarzschild solution. All the mass concentrated at a single point in space. Space-time curves to infinity at that point from all directions. But most real black holes rotate. They have to, because the stars they formed from were rotating. When a rotating star collapses, its rotation speeds up dramatically, like a figure skater pulling in their arms during a spin. The resulting black hole can be spinning at a significant fraction of the speed of light. For a rotating black hole, the solution is called the Kerr solution, discovered by Roy Kerr in 1963. And in this case, the singularity has a different shape. Instead of a point, it's a ring. A circular loop with zero thickness, but a definite radius. The faster the black hole rotates, the larger the ring. A ring singularity is just as problematic as a point singularity. The mass is still concentrated into zero volume. It's just spread around a circle instead of at a point. The density is still infinite. The space-time curvature is still infinite along that ring. Here's something deeply strange to contemplate. Inside the event horizon, the singularity isn't even really ahead of you in space. It's ahead of you in time. Once you cross the event horizon, the radial direction, the direction pointing toward or away from the singularity, becomes time-like. It becomes more like the temporal direction from past to future than like a spatial direction you can move back and forth in. This is hard to visualize because we have no experience with directions in space becoming directions in time. But mathematically, it's what happens. Inside the event horizon, space and time trade roles. The singularity is not a place you move toward. It's a moment you move toward, as unavoidable as the next tick of your clock. You cannot avoid reaching the singularity any more than you can avoid reaching next Tuesday. It lies in your future. And when you reach it, when you arrive at that moment where curvature becomes infinite, something happens. Something that breaks every law of physics we know. Chapter 10. Space-time. Curvature goes infinite. To understand what infinite curvature means, we need to think carefully about what curvature is. When we say space-time is curved, what exactly are we saying? Imagine you're walking on the surface of Earth. You walk in what feels like a straight line, never turning left or right. But if you keep walking in that same direction long enough, you'll eventually come back to where you started. You've walked in a circle around the globe. The surface is curved, and that curvature means that what feels like a straight line is actually bent into a loop. That's positive curvature, curving like the surface of a sphere. Space-time near a massive object has similar positive curvature. What appears to be a straight path through space-time, a path followed by a freely falling object, is actually curved by the presence of mass. Far from a black hole, this curvature is gentle. It's like rolling hills on the landscape. You notice the slopes, but they're not extreme. A planet orbiting a star far away follows an almost circular path, gently curved by the star's mass. Closer to the black hole, the curvature becomes steeper. Now it's like being on a mountainside. The slopes are sharp. An orbit closer in has to move faster to avoid falling inward, because the curvature is pulling more strongly. At the event horizon, the curvature becomes vertical. It's like standing at the edge of a cliff. There's no more gentle slope. The direction toward the singularity becomes a straight drop. This is why nothing can escape. Climbing out would require moving in a direction that doesn't exist anymore, like trying to walk straight up a vertical wall. But the singularity is worse than a cliff. Much, much worse. At the singularity, curvature becomes infinite. It's not just steep. It's infinitely steep, which doesn't even make sense in our normal understanding of geometry. Think about it this way. Curvature measures how much straight lines deviate from what they do in flat space. On a flat surface, if you draw two parallel lines and extend them forever, they stay parallel forever. On a curved surface like a sphere, lines that start parallel will eventually meet. The more curved the surface, the faster they converge. At infinite curvature, parallel lines don't just meet quickly, they meet instantly. Or perhaps they can't even be defined as separate lines in the first place. The usual rules of geometry simply stop working. Distances become meaningless. What does it mean to measure the distance between 2 points when the space between them has infinite curvature? The path connecting them would have to bend infinitely sharply, which is not a path we can make sense of. Directions become undefined. If you could somehow survive to the singularity and point in some direction, asking how far is it that way, there would be no answer. The concept of that way breaks down when curvature diverges. Even the notion of points in space-time becomes questionable. We think of space-time as a smooth continuum, infinitely many points arranged in a continuous fabric. But at the singularity, this fabric tears. There's a boundary, an edge beyond which space-time simply doesn't exist in the way we understand it. Einstein's equations of general relativity are partial differential equations. They tell us how space-time curves in response to matter and energy. But at the singularity, these equations produce infinities. They essentially throw up their hands and say, "I don't know." The equations that work so beautifully everywhere else in the universe fail at this one crucial point. This is deeply troubling. It means our best theory of gravity, a theory that has passed every experimental test we've thrown at it, tells us there's a place where physics breaks down, where the universe contains a point that cannot be described by our laws of nature. Some physicists think this means singularities don't actually exist. They're artifacts of pushing general relativity too far into a regime where it should no longer apply. Others think singularities are real, but that new physics we haven't discovered yet, takes over at the singularity and resolves the infinities. The truth is, we don't know. And that uncertainty points to the biggest unsolved problem in all of theoretical physics. Chapter 11. Where physics breaks down. General relativity is not the only fundamental theory in physics. There's another one, equally important, equally successful. It's called quantum mechanics, and it describes the behavior of matter and energy at the smallest scales. Quantum mechanics is strange in its own ways. It tells us that particles don't have definite positions until we measure them. That particles can be in two places at once. That empty space isn't really empty, but seethes with virtual particles popping in and out of existence. It's counterintuitive, bizarre even, but it works. Quantum mechanics is the foundation of modern technology, from computer chips to lasers to MRI machines. Here's the problem. General relativity and quantum mechanics are incompatible. They're both right in their domains, but they contradict each other when you try to apply both at the same time. General relativity treats space-time as smooth and continuous. Quantum mechanics says that at small enough scales, everything becomes grainy and probabilistic. General relativity is deterministic. Given the present state, the future is fixed. Quantum mechanics is probabilistic. We can only predict chances of different outcomes. For most situations, this incompatibility doesn't matter. General relativity handles big things like planets and galaxies. Quantum mechanics handles tiny things like atoms and photons. The two theories work in different domains, so they don't interfere with each other. But at a singularity, both theories should matter. A singularity involves an enormous amount of mass, so general relativity is important. But that mass is concentrated in zero volume, which means we're talking about incredibly tiny scales where quantum effects should dominate. We need a theory of quantum gravity, a theory that unifies general relativity and quantum mechanics into a single framework. We've been trying to create such a theory for nearly a century, and we still don't have one that works. There's a scale where this unification becomes absolutely necessary. It's called the Planck scale, named after Max Planck, one of the founders of quantum mechanics. The Planck length is incredibly tiny, about 10 to the minus 35 meters. That's a decimal point, followed by 34 zeros, and then a 1. For comparison, an atom is about 10 to the minus 10 meters, so the Planck length is about 10,000 trillion times smaller than an atom. At the Planck scale, quantum fluctuations in space-time itself become important. Space and time don't just curve smoothly, they foam and fluctuate. The nice, continuous fabric we imagine becomes a boiling, chaotic quantum foam where the notions of distance and duration lose their usual meanings. Near a singularity, we inevitably reach Planck scales. As matter gets compressed to higher and higher densities, we eventually reach densities where quantum gravity effects must take over. But without a working theory of quantum gravity, we can't say what happens. Several candidates for quantum gravity exist. String theory proposes that fundamental particles are actually tiny, vibrating strings. In string theory, singularities might be resolved, replaced by tiny but finite-sized objects. The point at the center of a black hole would actually be a string-sized region, small beyond human comprehension, but not truly zero-sized. Loop quantum gravity takes a different approach, suggesting space-time itself is made of discrete chunks at the Planck scale, like pixels on a screen. In this theory, you can't compress matter infinitely because there's a minimum possible size. The singularity would be replaced by a region of maximum density but finite size. Both theories and others are still highly speculative. We have no experimental evidence for any of them. The energies needed to probe the Planck scale directly are fantastically beyond anything we can create in laboratories. It would take a particle accelerator the size of the entire galaxy to reach those energies. So we're stuck with a profound uncertainty. Our best classical theory, general relativity, predicts singularities where physics breaks down. Our quantum theories suggest those singularities might be resolved by quantum effects. But we can't calculate exactly what happens because we don't have the right equations yet. This is the frontier of physics. The singularity represents the edge of human knowledge, a place where our understanding quite literally reaches its limit. And admitting that we don't know is not a failure, it's honesty. It's the recognition that nature still has deep secrets we haven't uncovered. Chapter 12. What happens to matter at the singularity? Even without a complete theory of quantum gravity, we can ask what happens to matter as it approaches the singularity. What is the fate of the atoms and particles that fall into a black hole? Remember, tidal forces become arbitrarily strong as you approach the singularity. These forces will tear apart any structure held together by ordinary physical forces. Your body first, then your cells, then molecules, then atoms themselves. An atom is mostly empty space. The nucleus, containing protons and neutrons, is about 10,000 times smaller than the atom itself. The electrons orbit this nucleus in probabilistic clouds. The atom is held together by electromagnetic forces, the attraction between positive nucleus and negative electrons. As tidal forces grow, even these electromagnetic forces become insufficient. The nucleus gets pulled away from the electron clouds. The atom is ionized, torn into ions and free electrons. But that's just the beginning. The nucleus itself is held together by the strong nuclear force, the most powerful force in nature at short distances. This force binds protons and neutrons together into the nucleus, overcoming the electromagnetic repulsion between positively charged protons. It takes enormous energy to break these bonds. But near the singularity, tidal forces eventually exceed even the strong force. The nucleus itself gets ripped apart. Protons and neutrons separate. We now have a soup of individual nucleons and electrons, all falling toward the singularity. But we can go deeper. Protons and neutrons are not fundamental particles. They're made of quarks, bound together by particles called gluons. A proton contains 3 quarks, bound so tightly that we've never observed a free quark in nature. The strong force actually gets stronger as you try to pull quarks apart, like a rubber band that resists more the more you stretch it. Yet even this binding has limits. Near enough to the singularity, tidal forces overwhelm even the quark-gluon bonds. The protons and neutrons themselves disintegrate into their constituent quarks and gluons. We now have a plasma of fundamental particles, the most basic building blocks of matter as we know them, all still falling inexorably toward the singularity. What happens next? Do the quarks themselves get torn apart, revealing even more fundamental structure? Or are they truly fundamental, indivisible? If they are fundamental, what happens to them at the singularity? One possibility is that all the information about the particles, their quantum states, their properties, everything that made them distinct, is simply destroyed at the singularity. The particles cease to exist in any meaningful sense. They're erased from the universe. But this raises a serious problem called the information paradox. Quantum mechanics says that information cannot be destroyed. The state of a quantum system at one time determines its possible states at all future times. If information is destroyed at a singularity, quantum mechanics is violated. Stephen Hawking spent much of his career wrestling with this paradox. In the 1970s, he discovered that black holes aren't entirely black. Due to quantum effects near the event horizon, black holes actually emit radiation, now called Hawking radiation. This radiation is extremely faint, negligibly small for large black holes, but over enormous spans of time, a black hole will gradually evaporate away. The question is, does Hawking radiation carry away the information about what fell into the black hole? Or is the information lost forever? Hawking initially believed information was destroyed, but later changed his mind. Most physicists now believe information must be preserved somehow, perhaps encoded in subtle correlations in the Hawking radiation, though exactly how this works is still debated. Another possibility involves the holographic principle. This radical idea suggests that all the information about what's inside a black hole is actually encoded on the event horizon itself, like a hologram encodes three-dimensional information on a two-dimensional surface. From this perspective, matter doesn't really fall to the singularity at all. Its information gets smeared over the horizon. The truth is, we don't know what happens to matter at the singularity. We know it gets compressed, torn apart into ever smaller constituents. But the final fate, what happens at truly zero size, if such a thing exists, remains one of the deepest mysteries in physics. And if matter's fate is uncertain, the implications for fundamental concepts like causality become even stranger. Chapter 13. Causality breaking down. We've talked about space and time, mass and energy, curvature and density. But there's another fundamental concept that comes under assault near a singularity. Causality, the idea that cause precedes effect, that the past determines the future, that events unfold in a logical, sequential order. In our everyday experience, causality seems absolute. You drop a glass, then it shatters. The dropping causes the shattering. Never do we see glass shards spontaneously assemble themselves and leap up into your hand. Time has a direction, an arrow, always pointing from past to future. General relativity has something to say about this. In curved space-time, there are paths called time-like curves. These are paths that massive objects can travel along, always moving slower than light. Your own life traces out a time-like curve through space-time. You move forward in time, potentially moving through space as well, but always remaining at each moment slower than light speed. In normal space-time, time-like curves only go forward in time. Your path takes you from past to future, always. But in extremely curved space-time, near certain kinds of singularities, something bizarre becomes possible. Close time-like curves. Paths through space-time that loop back on themselves. Imagine following a path through space-time, always moving forward into your future, never exceeding light speed. But because space-time is curved so severely, your forward path eventually brings you back to where and when you started. You arrive back at the same moment you left. You meet your younger self. This is time travel, not in the science fiction sense of a machine that transports you, but as a consequence of space-time geometry. The path you followed was perfectly valid. You always move forward into your future, but that future looped back to your past. Closed time-like curves create paradoxes. The most famous is the grandfather paradox. If you travel back in time and prevent your grandparents from meeting, you're never born. But if you're never born, you can't travel back to prevent their meeting. Contradiction. Physicists take these paradoxes seriously. They suggest that something must prevent closed time-like curves from being physically real, even if they're mathematically allowed by general relativity. Stephen Hawking proposed the chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel paradoxes. How might chronology be protected? One possibility is that quantum effects become infinite along any closed time-like curve, creating a sort of quantum barrier that prevents you from completing the loop. Another is that closed time-like curves are simply unstable. They collapse or change their geometry before they can be traversed. But here's the unsettling part. We don't know for sure that closed time-like curves are impossible. General relativity allows them in certain situations, particularly in rotating black holes. Without a complete theory of quantum gravity, we can't definitively rule them out. Inside the event horizon of a rotating black hole, space-time becomes even more exotic than around a non-rotating one. There are regions where time and space mix in bizarre ways, where the distinctions between past and future become blurred. At the singularity itself, where curvature becomes infinite, causality may break down completely. What does it even mean to say that event A causes event B when time itself has lost its meaning? When past and future are no longer clearly defined? This is not just an abstract philosophical question. If singularities exist and causality breaks down at them, it means the universe contains points where prediction is impossible, where, given the present state, we cannot, in principle, determine the future, where events can happen without causes or effects can precede their causes. Most physicists find this deeply troubling. Science is built on the idea that the universe is predictable, that it follows rules, that if we know enough about a system, we can forecast its behavior. A singularity where causality breaks down threatens this foundation. But nature doesn't care about our discomfort. If singularities are real, we have to accept what they imply. Or we have to find new physics that prevents true singularities from forming in the first place. Chapter 14, Rotating Black Holes. The Kerr solution. Most of what we've discussed so far applies to the simplest type of black hole, a non-rotating one described by the Schwarzschild solution. But real black holes, the ones that actually exist in nature, are almost certainly rotating. When Roy Kerr found the solution for a rotating black hole in 1963, it was a mathematical tour de force. Einstein's equations are notoriously difficult to solve exactly, and finding a solution for a rotating black hole had eluded physicists for nearly 50 years after Einstein published General Relativity. The Kerr solution reveals that rotating black holes have a much richer structure than non-rotating ones. Let's walk through this structure from outside to inside. Far from the black hole, space is curved much like around a non-rotating black hole. But there's an additional effect, frame dragging. The spinning black hole drags space-time around with it, like how a spinning ball in honey would drag the honey around. Objects near the black hole get swept along by this dragging effect, even if they're not in orbit. Closer in, you encounter the ergosphere. This is a region outside the event horizon where frame dragging becomes so strong that nothing can remain stationary. Even if you fire your rockets at full power trying to hover in place, you get swept around the black hole. You're forced to rotate in the same direction the black hole spins. The ergosphere has an outer boundary called the static limit. Outside the static limit, you can hover. Inside, you must move. The ergosphere is not the event horizon. You can still escape from the ergosphere. It's just that while you're there, you cannot stay still. Now we reach the event horizon. But for a rotating black hole, the event horizon is not a perfect sphere. It's slightly flattened, more like an oblate spheroid, bulging at the equator and flattened at the poles. The faster the black hole spins, the more distorted it becomes. Crossing this outer event horizon, you might expect to reach the singularity immediately. But in a Kerr black hole, there's more structure inside. There's an inner event horizon, a second boundary within the outer one. Between the outer and inner horizons lies a region of intense weirdness. Here, energy can be negative relative to the outside universe. This region is likely unstable. Any small perturbation, any bit of matter or energy falling in, probably causes this region to collapse or transform. But mathematically, it's there in the solution. Pass through the inner horizon and you reach the singularity. But remember, for a rotating black hole, the singularity is not a point. It's a ring. All the mass of the black hole is concentrated on this ring-shaped curve, spinning at incredible speed. Here's where things get really strange. The mathematical solution suggests that if you approach the ring singularity carefully, you might pass through the ring rather than hitting it. And on the other side, you would emerge into a different region of space-time. The equations suggest this region is a white hole, the time reverse of a black hole. While nothing can escape from a black hole, nothing can enter a white hole. Matter and light are expelled from it. It's like watching a black hole's formation running backward. Beyond the white hole, the solution extends into another complete universe, or perhaps another region of our universe far removed from the black hole you entered. In principle, you could use the rotating black hole as a kind of tunnel, a bridge connecting different parts of space-time. This sounds like science fiction, and most physicists believe it is fiction. The regions inside the inner horizon are almost certainly unstable. Real black holes receive a constant influx of radiation from the cosmic microwave background, from starlight, from the quantum vacuum. This radiation would accumulate at the inner horizon, creating huge, possibly infinite energy densities. When you factor in these realistic complications, the inner structure probably collapses. The ring singularity is likely replaced by a chaotic, churning mess of extreme curvature. The tunnel to another universe almost certainly doesn't exist in practice, even if the idealized mathematical solution allows it. But the fact that general relativity even permits such exotic structures is remarkable. It shows just how strange space-time can become under extreme conditions, and it hints that black holes, especially rotating ones, might have surprises we haven't imagined yet. Chapter 15. Naked Singularities. Throughout this journey, we've assumed that every singularity is hidden behind an event horizon. This is a comforting thought. If singularities are places where physics breaks down, where the laws of nature fail, at least they're hidden from the rest of the universe. We can't see them directly. They can't affect us. They are safely tucked away behind the one-way membrane of the event horizon. But what if this assumption is wrong? What if singularities can exist without event horizons? What if the universe contains naked singularities, exposed to view, with nothing hiding their infinite curvature from the rest of space-time? This possibility terrifies physicists. A naked singularity would be visible to outside observers. Light could escape from it. And more troublingly, unpredictable, possibly arbitrary events could emerge from it and affect the rest of the universe. Think about what this means. A singularity is a place where our equations break down, where we cannot make predictions. If that singularity is hidden behind a horizon, it doesn't matter. Whatever happens at the singularity stays at the singularity. The event horizon acts as a protective shield, preventing the unpredictable region from contaminating the predictable universe outside. But a naked singularity has no such shield. Events at the singularity could influence the wider universe. And since we can't predict what happens at the singularity, we can't predict how it will affect space-time around it. We lose the ability to forecast the future based on the present. This is called the cosmic censorship hypothesis, proposed by Roger Penrose in 1969. Cosmic censorship says that nature abhors naked singularities, that they're forbidden by some as yet unknown law of physics. Whenever a singularity forms, an event horizon must form around it to hide it from view. For decades, most physicists believed cosmic censorship must be true. The alternative was too disturbing to contemplate. A universe where naked singularities exist would be a universe where fundamental predictability breaks down. Science itself would be threatened. But belief is not proof. Can we prove that naked singularities are impossible? It turns out this is an extraordinarily difficult question to answer. General relativity itself doesn't forbid naked singularities. There are solutions to Einstein's equations that contain them. For example, if you could somehow spin a black hole fast enough, the mathematics suggests the event horizon might disappear, exposing the ring singularity. Or, if you arranged matter in just the right way and let it collapse, you might create a naked singularity directly without ever forming an event horizon. These scenarios are highly artificial. They require precise conditions that seem unlikely to occur in nature. But they're not mathematically impossible. And several studies in recent years have found increasingly realistic scenarios where naked singularities might form. Some researchers have found numerical solutions where a naked singularity appears during gravitational collapse, at least temporarily. Others have explored whether quantum effects might create naked singularities on microscopic scales. The jury is still out. If naked singularities do exist, they might be extremely rare. Perhaps they require such specific conditions that the universe has existed for billions of years without producing a single one. Or perhaps they form but are immediately surrounded by horizons, making them naked for only an instant. Or perhaps they're common, and we simply haven't recognized them yet. Could the Big Bang itself be considered a naked singularity? The beginning of the universe, if there was a definite beginning, involves all of space emerging from a singularity. That singularity had no event horizon. In a sense, we're all affected by that primordial naked singularity. The difference is that the Big Bang singularity lies in our past. We can't predict what comes out of it, but we can observe what did come out of it. A naked singularity in a black hole would lie in our present or future, and its unpredictability would be ongoing. The cosmic censorship hypothesis remains unproven. It's a conjecture, a hope, a belief that the universe is fundamentally predictable. Whether that hope is justified, whether nature truly censors her singularities, is one of the most important open questions in gravitational physics. And it brings us full circle to thinking about singularities not just in black holes, but in cosmology. Because the universe itself may have begun with a singularity, and understanding that cosmic singularity might be the key to understanding everything. Chapter 16. Different types of singularities. We've spent most of our journey exploring black hole singularities. But they're not the only kind of singularity predicted by general relativity. There's another type, vastly more important in some ways, that existed in the distant past, or that may exist in the far future. These are cosmological singularities. Let's start with the Big Bang. All available evidence suggests that the universe has been expanding for approximately 13.8 billion years. Galaxies are moving apart from each other. The farther away a galaxy is, the faster it's receding. This is not because galaxies are moving through space, but because space itself is expanding, carrying the galaxies along with it. If we run this expansion backward in time, we reach a moment where all the galaxies were closer together. Run it back further, and all the matter and energy in the universe was compressed into a smaller and smaller volume. Run it all the way back to the beginning, and you reach a singularity. The Big Bang singularity is not an explosion in space. It's an explosion of space. At the moment of the Big Bang, all of space was compressed to zero volume. The entire universe, everything that exists, emerged from this singularity. Time itself began at the Big Bang. There is no before the Big Bang, because time itself did not exist before that moment. This is deeply strange to contemplate. We're used to thinking of events as having causes that precede them in time. But the Big Bang has no cause in the traditional sense, because there was no time before it for a cause to exist in. Just like a black hole singularity, the Big Bang singularity is a place where general relativity breaks down. The equations produce infinities. The density of the universe was infinite. The temperature was infinite. The curvature of space-time was infinite. These infinities signal that we're missing something, that quantum gravity should take over and resolve the singularity into something more comprehensible. Many cosmologists believe that quantum effects in the first fraction of a second replaced the Big Bang singularity with something less extreme. Perhaps there was a bounce, where the universe contracted to a minimum size before expanding again. Or perhaps time itself becomes fuzzy and quantum-like at that early moment, so the question, what happened at time zero, becomes meaningless. But whether the Big Bang was a true singularity or something quantum-resolved, it was certainly an extreme state. The early universe was hotter, denser, and more curved than any black hole that exists today. Understanding the physics of that moment is crucial to understanding where everything came from. Now let's consider the future. Will the universe expand forever, or will it eventually stop expanding and begin to contract? The answer depends on how much matter and energy the universe contains, and on the properties of dark energy, a mysterious component that seems to be accelerating the expansion. If the universe expands forever, it will grow colder and more dilute. Stars will eventually burn out. Black holes will evaporate. The universe will approach a state of maximum entropy, a heat death where nothing interesting can happen anymore. This is a kind of singularity too, an end state, though not one involving infinite curvature. But if the universe contains enough matter, or if dark energy behaves differently than we think, expansion could reverse. The universe could begin contracting. All the galaxies would fall back toward each other. Space would shrink. Temperatures would rise. Eventually, everything would be crushed together in a big crunch, a mirror image of the Big Bang. The Big Crunch would be a singularity just like the Big Bang, but running in reverse. All of space collapsing to zero volume. All matter and energy compressed to infinite density. The end of time itself. Would this be the end of the universe, or could it bounce into a new Big Bang, starting the cycle over? These are questions we cannot yet answer. But comparing different types of singularities helps us understand what they have in common and how they differ. Black hole singularities are local. They exist at specific locations in space, surrounded by event horizons. You can stay far away from them and be perfectly safe. They're formed by gravitational collapse, when matter curves space-time so extremely that it creates a trapped region. Cosmological singularities are global. The Big Bang singularity wasn't at a location in space, it was everywhere at once, or rather, it was before space existed. These singularities involve the entire universe, not just a local region. They mark boundaries of time itself. But both types share common features. Both involve infinite or near-infinite curvature. Both represent places where general relativity breaks down. Both likely require quantum gravity to properly understand. And both represent the ultimate frontiers where our knowledge reaches its limit. Understanding any type of singularity helps us understand all singularities. The quest to understand what happens at the center of a black hole is intimately connected to the quest to understand how the universe began. They're different aspects of the same fundamental mystery, the mystery of what happens when gravity becomes so extreme that space-time itself breaks. Chapter 17. Observing black holes in nature. Throughout this journey, we've been exploring theoretical predictions, mathematical solutions, thought experiments. But black holes are not just theory. They're real objects that exist in nature. We've observed them, we've studied them, and every observation we make teaches us something new about these extreme objects. Of course, we cannot observe a singularity directly. By definition, if it's hidden behind an event horizon, no light from it can reach us. But we can observe the effects of black holes on their surroundings, and those effects are dramatic. When matter falls toward a black hole, it doesn't just plunge straight in. It typically spirals inward in an accretion disk, like water swirling down a drain. As the matter spirals closer and closer to the event horizon, it accelerates to tremendous speeds. Friction between particles in the disk heats the material to millions of degrees. At these temperatures, matter emits X-rays, high-energy radiation that we can detect with X-ray telescopes in space. Some of the brightest X-ray sources in the sky are black holes with accretion disks. By studying the X-rays, we can measure the mass of the black hole, how fast it's spinning, and even the temperature of the disk at different distances from the horizon. One of the most famous black holes is Cygnus X1, discovered in the 1970s. It's a stellar mass black hole about 15 times more massive than the Sun, pulling material off a companion star. The X-rays from its accretion disk vary rapidly, flickering in milliseconds, telling us about the turbulent conditions near the event horizon. At the centers of most galaxies, including our own Milky Way, sit supermassive black holes, millions to billions of times the mass of the Sun. The one at the center of our galaxy, called Sagittarius, a star, weighs about 4 million solar masses. We've watched stars orbit around it for decades, mapping out its gravitational influence. Those stars move at thousands of kilometers per second, held in orbit by the black hole's immense gravity. In 2019, the Event Horizon Telescope collaboration released the first actual image of a black hole. Not just detecting its effects, but creating a picture. The target was the supermassive black hole at the center of the galaxy, M87, about 55 million light-years away. This black hole is 6.5 billion times the mass of the Sun. The image shows a bright ring of glowing gas surrounding a dark center. That dark center is the shadow of the event horizon. The event horizon itself is invisible, but it blocks light from the material behind it, creating a silhouette. The ring is the accretion disk, seen edge-on, with light bent around the black hole by extreme space-time curvature. This image was a triumph of observational astronomy. It required linking radio telescopes around the entire Earth into a single vast array, and it confirmed that the event horizon has exactly the size and shape predicted by general relativity. Einstein's century-old equations passed yet another test. In 2022, the same team released an image of our own galaxy's supermassive black hole, Sagittarius A star. It looks remarkably similar, a glowing ring around a dark shadow, despite being much smaller and closer than the M87 black hole. But perhaps the most exciting observations have come from gravitational wave detectors like LIGO and Virgo. These instruments detect ripples in space-time itself. created when massive objects accelerate violently. In 2015, LIGO made the first detection of gravitational waves, produced by two black holes merging together. When black holes orbit each other, they emit gravitational waves, losing energy and spiraling closer together. Eventually, they merge into a single larger black hole in a cataclysmic event that releases more energy than all the stars in the visible universe combined, though almost all of that energy is in gravitational waves, not light. The gravitational wave signal from a merger lasts only a fraction of a second, but it contains enormous information. We can measure the masses of both black holes before merger, the mass of the final black hole after merger, how much energy was released, and how fast the final black hole is spinning. We can test whether the merger behaves exactly as general relativity predicts. And so far, every merger we've observed matches Einstein's equations perfectly. The black holes ring like bells after merging, emitting gravitational waves at specific frequencies determined by their mass and spin. These ring-down frequencies match theoretical predictions to exquisite precision. We've now detected gravitational waves from dozens of black hole mergers. We've learned that black holes come in a wide range of masses. We've discovered that mergers are surprisingly common, happening somewhere in the observable universe, perhaps once every few minutes. We've even detected mergers involving black holes, much more massive than we thought could form from single stars, suggesting they might have grown through earlier mergers. Each observation gives us confidence that our theoretical understanding of black holes is correct. The event horizon exists. Space-time curves around black holes exactly as Einstein predicted. And by studying black holes in nature, we're testing general relativity in the most extreme conditions possible outside of a singularity. We cannot see the singularity itself. Perhaps we never will. But by studying everything around the event horizon, we're learning what must lie within. We're mapping the territory right up to the edge of the unknowable. Chapter 18. The big questions remain. We've traveled together on an extraordinary journey. We started with simple gravity, the force you feel every day pulling you toward Earth. We discovered that gravity isn't a force at all, but the curvature of space-time. We followed that curvature to its most extreme manifestation. Black holes, where space-time curves so steeply that it traps light itself. We crossed the event horizon, that point of no return, and discovered that crossing it is smooth and unremarkable to someone falling through, even as it appears to take forever from outside. We encountered tidal forces that rip matter apart, stretching it like spaghetti, breaking it down into ever smaller constituents. And finally, we arrived at the singularity itself, the point where curvature becomes infinite, where all our equations break down, where physics as we know it reaches its absolute limit. We found a place that defies understanding, that exists at the boundary between what we know and what we can never know with our current theories. Let's be honest about what we've learned and what we haven't. We've learned that general relativity, Einstein's theory of curved space-time, is remarkably accurate. It describes gravity beautifully everywhere we've tested it, from GPS satellites to gravitational wave detections to the shadows of black holes. We have every reason to trust what it tells us about space-time near the event horizon. But we've also learned that general relativity is incomplete. At the singularity, it produces infinities and breaks down. We need a theory of quantum gravity, a theory that unifies general relativity with quantum mechanics, to understand what really happens at the center of a black hole. We don't have that theory yet. String theory, loop quantum gravity, and other approaches offer possibilities, but none are confirmed by experiment. We may not have a complete theory for decades or longer. The energy scales involved are so extreme that direct experimental tests may be impossible with any conceivable technology. So what remains unknown? The list is long and humbling. We don't know if singularities are truly points of infinite density, or if quantum effects resolve them into something finite but very small. We don't know exactly what happens to information when it falls into a black hole. Does it get destroyed, violating quantum mechanics? Or is it preserved somehow, encoded in subtle correlations in Hawking radiation, or on the event horizon itself? We don't know if naked singularities can exist, exposed to the universe without event horizons to hide them. We don't know if the exotic internal structure of rotating black holes, the ring singularities and inner horizons, can survive in realistic scenarios, or if they collapse into chaos. We don't know if closed time-like curves, paths through space-time that loop back on themselves allowing time travel, are possible even in principle. We don't know if the laws of physics protect causality or if they permit paradoxes under extreme conditions. We don't know how the Big Bang singularity relates to black hole singularities. Did the universe truly begin from an infinitely compressed state, or was there something before? Could our entire universe have emerged from inside a black hole in another universe? Could black holes in our universe contain baby universes of their own? These are not just academic questions. Understanding singularities is crucial to understanding the deepest nature of space, time, matter, and energy. It's the ultimate frontier of physics, the place where all our theories converge and all our understanding reaches its edge. But here's the exciting part. We're not giving up. Right now, new telescopes are being built that will image black holes with even higher resolution. The Event Horizon Telescope is being expanded with more observatories, allowing us to create videos of black holes, watching the accretion disk swirl in real time. Gravitational wave detectors are being upgraded to detect more mergers and more distant events. Future detectors in space will be sensitive to supermassive black hole mergers, events so energetic they shake the entire observable universe. Each detection teaches us something new about how black holes behave. Theoretical physicists are developing new approaches to quantum gravity. Computer simulations are exploring black hole interiors with increasing sophistication. Mathematical physicists are discovering new solutions to Einstein's equations, finding new ways that black holes can form and interact. Maybe one day we'll have a complete theory of quantum gravity. Maybe we'll understand exactly what happens at a singularity. Maybe we'll even find a way to extract information from black holes, to peer inside and see what we've been trying to understand all along. Or maybe singularities will remain forever at the edge of knowability, places where the universe guards its deepest secrets. Maybe there are fundamental limits to what we can understand, boundaries built into the structure of reality itself that we can approach but never cross. Either way, the quest continues. Science is not about having all the answers. It's about asking better and better questions, pushing further and further into the unknown. Every generation of scientists builds on what came before, reaching a little further, understanding a little more. The singularity represents the ultimate challenge to human understanding. It's a place where the familiar concepts of space and time, cause and effect, matter and energy all break down. It's where the universe becomes truly alien, truly incomprehensible with our current frameworks. But that's what makes it so fascinating. That's what drives us to keep exploring, keep calculating, keep observing. Because somewhere out there in the darkness, at the hearts of black holes scattered throughout the cosmos, these singularities exist. They're real features of our universe, not just mathematical abstractions. Understanding them means understanding something fundamental about reality itself. It means completing the revolution that Einstein began over a century ago. It means finally answering the question of what happens when gravity is pushed to its absolute extreme. We may not have all the answers yet. We may not have them for a long time. But we're asking the right questions. We're using the best tools we have. We're pushing human knowledge to its limit and beyond. And in the end, that's what science is all about. Not certainty, but curiosity. Not final answers, but endless questions. Not the comfort of what we know, but the thrill of what we have yet to discover. The singularity waits at the heart of the cosmic abyss, a mystery wrapped in an event horizon, a challenge to everything we think we understand about the universe. And somewhere out there, in the depths of a black hole too distant for us to ever reach, time ends, space curls back on itself, and reality breaks apart into infinity. We cannot go there. We cannot see what happens, but we can imagine. We can calculate. We can observe from afar and piece together the clues. We can stand at the edge of human knowledge and peer into the darkness, wondering what secrets the universe keeps at its most extreme. This is our journey. This is the quest to understand what happens to space-time near a singularity. It's a journey that may never be complete, a question that may never be fully answered. But it's a journey worth taking, because it takes us to the very edge of what is possible, to the boundary between the known and the unknowable, to the place where the universe itself breaks down and demands that we think harder, look deeper, and never stop searching for truth. That's where discovery begins, at the limit of what we know, at the edge of the cosmic abyss, at the singularity.